Welcome back, everybody. Dr. Schoffer speaking here. I tried to cover this chapter in 2 segments, but my software slowed down and I didn't want to risk losing all the recording, so I cut it off. So we're just going to finish up rather quickly what is yet left to cover in here. Basically, there are 3 more parts, although they're rather brief. We're just going to look at proton NMR, and just at aromatics, and I'll show you something that can help you in making assignments. Then we're going to move on to carbon-13, and you know the good news about carbon-13, many of the things we learn about the chemical shift is going to apply to carbon-13 in a similar fashion, just on a broader scale, because the chemical shift, for proton, it's going to range, most of the signals will be in the range of 12 to 0. But when we're looking at carbon-13, we're dealing with 250 ppm to 0 ppm. And then there's a very special but very powerful technique. You're going to find maybe a couple of them in your homework assignment, and maybe one question in your quiz, and that is DEPT. And this is a fancy acronym. We'll talk about a little bit about this. So not many more slides to come, but also again emphasis that you need to read the book and you need to work as many problems as possible until you get that aha moment. And you don't have to do segment A through H. Maybe you understand the concepts well enough by working in the first 2 or 4 problems, and then you can move on to the next segment. Okay, so we can use proton NMR to distinguish between compounds, and the 3 molecules we have here below, they couldn't really be distinguished by IR or mass spec, and that's why NMR is one of the most powerful methods. What I really want to draw your attention to right away is that when we're looking at the aromatic ring, which is shown here, remember how we can draw a resonance structure? That this double bond, can also be reassigned to here. We can draw a resonance structure. This can be reassigned to here, and we're going to have 2 chapters covering the chemistry of aromatic compounds. We're going to have to really have very good foundational knowledge. Because of this resonance that we have in these structures, it's actually very helpful in the proton and carbon-13 analyses that we draw it maybe as a circle. I know I have some colleagues who really object to using this kind of symbol, but this really represents that we're dealing not just with a double, single, double, single, double, single bond, but really about an average of a 1.5 bond order between a single and a double all around, okay? And that helps us to better understand the symmetry in the structures. Let me see whether I can draw the first example here. So we could redraw the first structure, put the circle in here, and it's a crooked one, pardon me. And then we have 2 methyl groups, okay? And then the other hydrogens. And what you want to do is look for symmetry. And it's very clear that we can cut the structure in half. Sometimes you need to rotate your molecule, maybe redraw it in a certain way so you can see the symmetry. Which means that if I was to analyze this according to our proton NMR, I would have position A, no hydrogen here, there's a hydrogen here, B, and then there's a hydrogen here, C, and I would repeat that on the other side. So we have A, and then we have B, and then we have C. So we would only expect 3 proton signals. And I really want to emphasize here, you need to be capable of seeing where symmetry is in a molecule. Maybe there's some, maybe there's none. But if there's symmetry, how it affects, and usually it cuts or it reduces the number of signals that you will see. Okay, so the next slide has sort of a summary with a given formula. And remember, you can always stop the video, work on additional problems, open your textbook, look at all the skill builders. This is really good investment of your effort to succeed in this class. So we had learned that as we're looking at a given formula, we can determine the structure here. With a series of untitled are there in. Look at the number of NMR signals, and we had learned a very important aspect, and again, they may play an important role. Analyze each signal and draw fragments consistent with each signal. You want to understand how the electronic environment is influenced, and then you assemble your fragments into a complete structure. And then you verify the structure by applying all the different skills. Sadly, students think that if they just memorize a whole bunch of stuff that they'll do well in this class. It's really a futile approach, because you really need to tap into your critical thinking skills in order to manage the vast amount of information, but also the very abstract and complex concepts where you have to apply your critical thinking skills, and please don't try to just memorize things, because there is a logic to all of this information. All right. Now, in proton NMR, we also say that proton NMR is very sensitive. You may want to make a note of that. Why? Because the most abundant isotope of hydrogen, the proton, we get really strong signals here. Okay, so abundance has something to do with effect. Now, when it comes to carbon-13, remember when we discussed mass spectrometry? We said that C12 is about 99% abundance, and here we only have 1%, which means we have to run a sample longer to get a stronger signal. And so we want to be really cognizant that this is far less sensitive. Okay. Now, in proton NMR, we said that the chemical shift, delta, the splitting with coupling constants J, and integrals are really important to give us the fragments of a molecule. Now, in carbon-13, we want to mostly focus on the signals and the chemical shift. And most signals are just going to be one peak, so singlets. Okay, so I'm going to discuss a couple more details about carbon-13 in the next few slides. All right, so in a carbon NMR, the hydrogen-carbon splitting is very complex and really not very effective. So we really reserve our splitting to the splitting analysis to proton NMR in here. Okay. Now, to figure out a carbon-13 spectrum and make it easier, really what is being done is, contrary to proton NMR, we actually running a decoupled spectrum, and that's why we only get signals, and that's much easier and more powerful to put together the pieces of a puzzle. So here you are. Singlets is what you're going to see. And then most of the time, the number of lines are often, they're equivalent to the number of carbons. And again, here's your keyword. You got to look for. On the next slide, you see here's I have some specialty software where I've kind of summarized again the chemical shift. You also have additional graphics in the textbook. I'll show you one in a couple of slides. So we use different frequency. This is the most important part, I think. Again, instead of going from 0 to 12 in a proton NMR spectrum, here we're going from 0 to actually about 250. But most of the material is going to show up by about 220, and that's where you can see this. Again, what upfield, downfield means, what the electronic effect